Representative reconstruction. The surf hisses, sand flies in curving sheets. A squad pushes up from a broken dune, faces squinting under smoke. For 30 seconds, everything narrows to a handful of actions. Shoulder, breathe, aim, press. A rifle snaps, the metal sings. And each time the soldier pulls the trigger, the bolt snaps back and returns without his hands. Leaving the pistol, grip-spent cases spit into the air. Another cartridge slides forward from a small metal packet, and the sights settle on a new target. Those 30 seconds are a door. In them, a squad finds time to form a line, to reach a nearby foxhole, to change the direction of an advance. The camera stays on one rifle, on the repeated click and the faint puff of gas above the barrel. It is a small mechanical heartbeat. It will be the difference between a squad being cut down and a squad living to fight another minute, another hour, another campaign. If you like deep historical tech stories, subscribe for more. The provocative claim in the title, The 30-Second Window, that decided the fate of civilization sounds grand, almost hyperbolic. The argument this film will make is more modest, and perhaps more persuasive. Not that one rifle alone determined the arc of history, but that a single, repeatable interval of sustained, aimed fire, bought by a particular mechanism and delivered again and again, by soldiers across battlefields, changed the odds in countless local fights. Those small victories and survivals aggregated. They altered unit cohesion, shifted momentum on beaches and ridgelines, reduced the frequency of chaotic retreats. In war, repetition matters. A dependable 30 seconds of effective fire, multiplied across hundreds of squads and thousands of engagements, becomes strategy. This is the story of how a self-taught mechanic at the Springfield Armory conceived and refined a gas-operated, semi-automatic rifle that could deliver that window, and of how American industry attempted to turn a clever mechanism into millions of service rifles before war demanded them. It is the story of John C. Garand, and of the M1 Garand machine, and the man of stubborn engineering, bureaucratic fights, and the uneasy moral ledger that tracks inventions that both protect and take lives. John C. Garand did not arrive at the armory as a celebrated genius. He arrived as an immigrant boy who loved gears. Born in a small Quebec village in the late 19th century and raised in the United States. He learned to make things by taking clocks apart, fixing small engines, and staring at how parts fit together. He was, by his own account, a tinkerer who read late into nights under a lamp, learning the small habits of metal and the patient arithmetic of mechanisms. Those habits would shape a lifetime. Garand's formal path into American ordnance began in the wake of the First World War. In 1919 he took a position at the Springfield Armory, the nation's long-established center of small arms design and testing. The armory was a place of methodical work, drawings, JIGS, long tests in the mud and cold, and a cautious bureaucracy that preferred incremental improvements to radical change. For a practical mind like Garand's, it was both a school and a laboratory. He taught himself the art of small arms by watching, by drafting, by building prototypes on his own time. He was not flamboyant, he was relentless. Over the next decade, his notebooks filled with sketches ideas for reducing the movements a rifleman had to make, for using the waste gas of a fired cartridge as the engine for the next mechanical step. The problem Garand set for himself was surgical. How to give an individual rifle the ability to deliver aimed follow-up shots quickly and reliably, without the shooter having to manipulate a bolt between each shot. Bolt-action rifles require a deliberate, sometimes awkward, sequence-open extract, cock, chamber, close that costs seconds and focus every time it must be repeated. In close quarters or under incoming fire, those seconds are expensive. The semi-automatic idea was not new in 1919, but making such a rifle durable, safe, and manufacturable at scale was an engineering crucible. At the heart of Garand's solution was a deceptively simple trade. Capture a small portion of the high-pressure gas that follows a fired bullet, and use that momentary pulse to drive a short mechanical motion that would do two things almost instantaneously: extract and eject the spent case, and chamber the next round. The visual metaphor he favored was not an engine's crank, but a human breath. Fire the cartridge. The barrel exhales a quick breath of gas. That breath pushes a tiny piston. The piston nudges a mechanism that turns the bolt, and the rifle is ready for the next shot. That short breath would need to move precisely, quickly, and without the long, heavy movements that made earlier gas systems clumsy or unreliable. One line, lay summary. The Garand used a short-stroke gas piston above the barrel to harness a tiny controlled portion of the firing gas to cycle the bolt automatically and feed the next round from an 8-trined N-block clip, creating a repeatable mechanical cycle measured in fractions of a second. Mid-level explanation. When a cartridge fires, the propellant burns and generates gas that propels the bullet down the barrel. At a small port located near the muzzle, a controlled amount of that gas is diverted into a cylinder containing a piston. That piston moves a short distance enough to transfer its energy into a separate operating rod or lever that causes the bolt to rotate, move rearward, eject the spent case, compress the return spring, strip the next cartridge from the N-block clip, and then lock the bolt forward again. Because the piston itself does not travel the full length of the bolt's motion, it is lighter and faster. The bolt's motion is completed by a separate mass that can be timed and cushioned to protect the parts and the shooter. This is the essence of a short-stroke piston system. Brief impulse, efficient transfer, rapid reset. Specific, measurable detail. Contemporary testing and Garand's own time measurements show the mechanical cycle for a single firing and reset could be on the order of 0.3 seconds under ideal conditions. That figure, about 0.3 of a second, represents the pure internal mechanical cycle time, not the human trigger pull rhythm, not the time to reacquire a moving target, and not accounting for mud, fouling, or battlefield stress. Even so, it provides a technical yardstick. If the mechanism could execute its internal cycle every 0.3 seconds, the machine could, in theory, complete roughly 100 cycles in 30 seconds. Practically, human factors and ammunition supply place strict limits on continuous firing. But the existence of such a rapid mechanical heartbeat gave soldiers the chance to produce short, effective bursts of aimed fire at a tempo that bolt actions could not match. Human impact sentence. That difference in tempo 3 skilled aimed shots in the time a bolt-action soldier had worked and re-aimed for one translates directly into the probability that a squad survives the next moment of contact. To see how this functions in practice, consider a compact thought experiment. A well-trained soldier with a bolt-action service rifle might get off to well-aimed shots in a tensioned encounter before having to operate the bolt. A soldier with a semi-automatic that cycles in 0.3 seconds can, with the same discipline to aiming, place 4 to 6 aimed shots in the same span. With controlled bursts and reloading considered, a squad equipped with semi-automatics can sustain suppressive fire for longer without exposing themselves to the pauses that invite counterattacks. The N-block clip that Garand favored holds 8 rounds, a compact, quick-loading packet that can be inserted and locked into the rifle in a single motion, but which still requires a brief manual action to reload once expended. Those design choices: short stroke, piston, N-block feeding. Sturdy receiver-balanced rapidity with simplicity and resilience. Garand's early experiments did not emerge fully formed. His initial prototypes used different piston lengths and placements, tried various positions for the gas port, and experimented with methods of securing the N-block clip. The first iterations, often referenced in armory records as test models, suffered predictable setbacks. In trials that aimed to simulate trench mud and tropical humidity, some designs stalled or jammed because deposits interfered with the piston's motion. Other variants worked well under clean conditions, but cracked or wore rapidly when fired repeatedly. There were also complications in mating the new action to the Army's choice of cartridge. For reasons of logistics and stopping power, the U.S. Army remained attached to the powerful .3006, round the same cartridge that had served through the First World War at least, until debates about lighter intermediate calibers began to surface. Adapting a semi-automatic mechanism to a high-pressure, Long-range round like the .3 U06 placed tight tolerances on the gas system. Too large a gas port and the mechanism would slam violently and break parts. Too small and it would fail to cycle reliably. The procedural history of testing reads like a ledger of both mechanical insight and bureaucratic friction. Garand's early versions, identified in armory logs as experimental types, were designated with code-like names. Initial models, T1E1 and then T1E2. They were sent to firing ranges, dunked in mud pits, and left in heat to test primer stability and metal expansion. Several designs failed in ways that were instructive. A gas port that eroded too quickly suggested the need for a hardened insert. A piston that carried heat into vulnerable pins taught the team to reroute thermal paths. An operating rod that flexed under continuous fire showed the need for stiffer metallurgy. Each failure refined the next drawing. These years also exposed the less mechanical obstacles to innovation. The interwar army operated under tight budgets, conservative procurement cultures, and the complex politics of the ordnance bureaucracy. Support for semi-automatic rifles waxed and waned as reports reached Washington. Some officers questioned whether a semi-automatic would survive the rough handling of enlisted troops. Others feared the logistical burden of changing calibers or training doctrines. There were also competing experiments across the world, other nations and private companies, pursuing alternative semi-automatic concepts. Garand and the Springfield Armory found themselves defending a practical design against both technical line skepticism and political caution. Despite the setbacks, incremental successes accumulated. Garand's short-stroke system began to show consistent cycling in controlled tests. The N-block clip-feeding system proved fast and mechanically simple, compared with some spring-fed magazines that had more parts to jam. The operating rhythm under clean conditions repeatedly returned times on the order of a few tenths of a second per cycle. These metrics mattered to men in foxholes and commanders in tents. Speed without reliability is a liability. Reliability without meaningful improvement is a poor investment. Garand's design, by combining speed with a compact clip system and a receptive shooter interface, started to look like an upgrade rather than a gamble. The adoption process was not a single dramatic green light, but a slow accumulation. Prototypes improved, tests persisted, and a chorus of endorsements from range officers and frontline trials began to appear in armory files. By the mid-1930s, after repeated redesigns and formal trials, the Army made a decisive move. The new service rifle was given an official designation and was adopted for procurement. The weapon received the designation most of us know today, the M1 Garand. That official adoption did not mean instant acceptance in every field manual or every officer's heart. It meant, rather, that the rifle had cleared enough technical and bureaucratic hurdles to enter the inventory. But adoption on paper raises a fresh, urgent question. Could American industry convert a hand-built prototype into millions of durable service rifles fast enough and at the quality demanded by soldiers? Design, acceptance, answers one set of problems. You have a sound mechanism under controlled conditions. Mass production answers another, repeatability under stress. Supply chains of materials, jigs and fixtures that translate hand-fitting into interchangeability, and the industrial discipline to hold tolerances across thousands of parts. The stakes were only theoretical in the 1930s. They became painfully practical by the late 1930s and early 1940s. Before production could be negotiated, several parallel problems needed resolution. One was material specification. The armory's craftsmen could fit parts by feel. A factory producing thousands of rifles had to control hardness, spring temper, and metallurgy so that a part stamped in Dayton and a part machined in Springfield behaved the same. Another was tooling. Semi-automatic actions require more precise surfaces and more complex assembly than simpler bolt actions. The Army and manufacturers, therefore, had to invest in new machines and skilled labor. And crucially, there was the training problem. Even the best weapon is only as effective as the hands that use it. Infantry doctrine, marksmanship, instruction, and small unit tactics would need to be adjusted to exploit the rhythm the M1 offered. It is tempting to compress these problems into a single fact about production totals. How many Garans were turned out in a year? How quickly were they shipped to frontline units? But the archival record contains a mix of precise figures and sources that conflict. Different manufacturers contributed in varying degrees. Springfield Armory remained the institutional heart of the design and early production. Private firms such as Winchester, Harrington, and Richardson, and large industrial concerns like International Harvester were later contracted to expand capacity. Wartime ramp-up would produce millions of rifles. Different sources report low to mid-millions as estimates. For the purposes of this narrative, let it suffice to say that by the early 1940s, American industry managed, with sweat and ingenuity, to scale production from experimental batches to mass manufacturing, that scaling would change the battlefield. The transformation from a shop-bound prototype to a mass-produced rifle did not happen overnight. It required rethinking processes. Jigs were designed so that a young machinist could place a part in the same way that a veteran craftsman used to do by sight. Quality control evolved from spot checks to systematic inspection. Tools that had been built for other industries were retooled to hold tolerances consistent with the Garand's receiver and bolt geometry. In many shops, thousands of men and women labored at stamping, heat-treating, and fitting. Early production runs exposed new faults. Parts that tolerated hand-fitting failed when produced on an assembly line. Finishes that resisted rust in a dry factory corroded in tropical shipping. Each problem demanded adjustments, hardening surface treatments, revised heat cycles, alternate alloys, and each adjustment temporarily slowed output. The management of these changes, the supply of steel and chromium and spring wire, and the training of workers were as decisive as the original sketches of piston and bolt. While the armory and manufacturers wrestled with these practical matters, the rifle did not remain an academic object. Soldiers and small unit leaders began to test the M1's potential in training grounds and against mock opposition. The key question was not whether the rifle made a soldier more lethal in some abstract sense, but whether it allowed a squad to maintain fire and cohesion during the brief, violent episodes that characterize infantry combat. The M1 promised two tactical advantages: a higher tempo of aimed fire per soldier and a psychological steadiness soldiers with semi-automatics could suppress. An enemy without repeatedly exposing themselves to operate the bolt. That steadiness is an underappreciated effect. In the disorienting minutes of a firefight, the confidence induced by a dependable automatic cycling can reduce hesitancy, shorten pause times, and ultimately reduce casualties. Soldiers' voices from letters and oral histories consistently emphasize small, vivid details rather than mechanical descriptions. One composite veteran testimony reads, "When all hell broke loose. Having that rifle meant you could keep your head down and your sights up. You didn't have to take your hand off the stock to work a bolt. Those are seconds that save you." That sentence, labeled here as a composite drawn from multiple veterans' accounts, reveals the practical psychology of the weapon. Its primary battlefield value often lay less in raw volume of lead and more in the ability to sustain focus through an exchange. Yet the mechanical and industrial triumphs were shadowed by ethical ambiguities. An instrument designed to increase survivability, for some inevitably increased lethality. Commanders measured such trade-offs, and soldiers experienced them in the immediate calculus of self-preservation and loss. Garand himself, when asked by contemporaries about his feelings toward the weapon's destructive uses, repeatedly framed his work as service an attempt to give soldiers a better chance to return alive. That framing, sincere and paternal, does not erase the moral complexities of inventions that select who lives and who dies on the margins. As the technical design matured and production began to scale, operational commanders started to receive the rifle in enough numbers to test its aggregate effects. Small unit encounters across different theaters began to provide material for comparison. Reports from training units described improved rates of medium-range engagements, fewer pauses in defensive fire, and a higher volume of sustained aimed firing in contested positions. These were not automatic strategic victories. They were local advantages that sometimes transformed the calculus of a skirmish. The central thesis of this narrative crystallizes here. If one soldier's 30 seconds become 2, 3, or 4 soldiers, repeated 30 seconds across numerous engagements, the cumulative effect on campaign tempo is real. Still, many questions remained unresolved by the mid-1930s and into the early years of large-scale production. How would the rifle perform in the North Atlantic rains, in the choking mud of hedgerows, in the tropical humidity of Pacific Islands? Would the en-bloc clip, which made reloading fast, prove a liability when the soldier needed to top up rounds from partial clips on the move? Could factories consistently deliver within the tolerances required for the gas system, or would an under-tempered spring erode reliability in the field? These were the worries that filled ordnance memos and labor planners' tables. One of the most persistent technical anxieties lay in the gas port itself. The very hole that made short-stroke operation possible was also a point of erosion. High-pressure gas, with small abrasive particles entrained, tended over tens of thousands of rounds to roughen the edges of a port and change how the piston received impulse. Armory engineers experimented with hardened steel inserts and new surface finishes to stabilize the port geometry under wear. They redesigned piston shapes to shed fouling more readily. Training emphasized cleaning routines and inspection schedules. Field manuals began to list the gas assembly as a critical check during cleaning rotations. These iterative, often tedious adjustments, hardening a face, changing the radius of a piston shoulder, tweaking spring rates aware, theoretical mechanism meets dusty reality. The social history that converged on the rifle's production is striking as well. In workshops, seasoned machinists taught new hires, and a wartime labor shortage pushed factories to recruit from previously untapped labor pools. The transition required both technical instruction and cultural adaptation. Workplace safety, inspection checklists, and the language of precision became common parlance for people who had never had to worry about micrometers or run-out. Companies that once made plows or agricultural equipment refocused on receivers and bolts. The War Department's contracting system, with its mix of fixed and incentive contracts, shaped the tempo of expansion. Payments and penalties fostered both speed and a tendency to conserve materials wherever possible. Those logistical choices, material substitutions, acceptance criteria, over time, schedules rippled into the final product. Even as factories labored, the political dynamic continued to shape procurement. Debates over caliber, doctrine, and training budgets were never fully resolved in paperwork. They were settled in field tests, in budget hearings, and ultimately in the urgency that came with global conflict. The mid-1930s adoption of the M1 did not mean unanimous enthusiasm. Some voices in the Army argued the complexity of a semi-automatic risked greater breakdowns in forward conditions. Others argued the increased rate of fire required new supply lines for ammunition, with attendant consequences for logistics. These arguments delayed full conversion, but they also forced engineers and planners to anticipate the downstream implications of a new standard-issue rifle. Representatives of the ordnance bureaucracy later pointed to a curious paradox. The very features that made the Garand desirable speed, semi-automatic ease of operation, a compact en-bloc, Fidelso, intensified the demand for disciplined training. A soldier with a semi-automatic had to learn controlled bursts, when to conserve ammunition, and how to maintain his gas system under duress. Training manuals had to evolve from merely how to hit the target to how to sustain fire as part of a squad. That doctrinal change may be less visible in photos of parades and armories, but it mattered on beaches and ridgelines. By the time the rifle entered full production in the late 1930s and early 1940s, a strange symmetry had emerged. The M1 was a machine that rewarded both mechanical soundness and disciplined human behavior. It favored those who took care of their equipment and who practiced fire control. It punished slapdash maintenance. The result was a weapon that, in the best of hands, could deliver a 30-second window of consistent, aimed fire more often than any bolt action could. Yet even as the technical and industrial threads knitted together, the human stories persisted, the small testimonies from letters home. The terse reports from company commanders describing a night defense where a single squad's steady fire bought time for a battalion to reorganize. These snapshots are the connective tissue between gears and outcomes. They are the reason a technical specification, a 0.3-second mechanical cycle matters, beyond the pages of engineering logs. At this juncture, with the rifle adopted and factories ramping, the narrative reaches a hinge. The design had proven its plausibility. The factories were learning to repeat the necessary processes. Manuals and training were adapting to a new rhythm of fire. But an even larger test loomed. Would these changes mechanical, industrial doctrinal hold, under the stress of actual combat in multiple theaters? The ultimate argument for the 30-second window is not made in workshops or in the quiet pages of a file cabinet. It is made where dust, rain, and fear conspire to create moments that last no longer than half a minute and yet decide whether a unit stands or breaks. The question that follows is stark. When those moments came in the mud of Normandy or in the tight jungles of the Pacific, did the Garand's 30-second window consistently deliver the tactical advantages its engineers promised? The answer unfolds, not in a single sentence, but across many accounts, many skirmishes, and many technical reports material that will be explored next. The answer to that question appears not in a single headline victory, but in dozens of small, tense moments recorded across diaries, after-action reports, and the scattered voices of veterans. To understand how the 30-second window operated on the ground, we must move from drawings and factory floors back into the dirt and smoke, where a rifle's temperament meets human fear. Representative reconstruction. A hedgerow cracks with rifle reports. A patrol moves low through a lane of churned earth. A sudden ambush folds the lead man like a hinge. For 30 seconds, the fight is a narrow corridor of motion men pressed down. Fingers find triggers. The rifle's rhythm becomes the unit's pulse. Where bolt-action soldiers pause to work bolts. Where command fragments into isolated bursts of frantic reloading. The squads armed with semi-automatics maintain a steadier voice. Those seconds do not create strategy by themselves, but they enable it. A fire team's steady bursts can hold a flank long enough for reinforcements to arrive, for artillery to be adjusted, for a commander to reorganize. This scene, marked as a representative reconstruction based on multiple accounts, repeats across theaters in forms specific to terrain, but similar in consequence. We can trace the rifle's tactical footprint in two overlapping ways. Microdynamics, what one soldier and his rifle could do in a half-minute-hand macro patterns, how repeated. Microdynamics altered small unit performance across campaigns. The microdynamics rest on the machine's mechanical heartbeat and the human practices around it. The macro patterns depend on scale. How many squads received the rifle? How well they were trained to use controlled bursts, and how logistics sustained the tempo of engagements. On the micro level, the key advantages were twofold. First, a semi-automatic reduces the mechanical interruptions that break a soldier's concentration. Each time you must operate a bolt, you remove a hand from the firing grip, change body position slightly, shift your eyes to the receiver, and then reacquire sights. Cumulatively, those interruptions are measured in seconds and in lost opportunities. Second, the rhythm of a semi-automatic encourages controlled fire discipline. Trained men can squeeze in short, accurate bursts 2 to 4 rounds without losing sight picture, then pause, evaluate, and fire again. This is not indiscriminate volume. It is repeated, aimed action. Representative calculation. Using the mechanical benchmark discussed earlier, the internal cycle measured in tenths of a second, unencumbered system can complete many cycles in 30 seconds. But a practical soldier does not fire continuously at the mechanical limit. Instead, he fires in short, deliberate bursts, conserving ammunition and preserving sight alignment. In practice, then, a well-disciplined trooper with an M1 might deliver 2 to 4 controlled 3-round bursts in a 30-second intense exchange, punctuated by brief adjustments. The key is that each burst is delivered with less physical interruption than a bolt action can manage, increasing the probability that aimed shots hit and that suppression holds. Turning to the macro level, historians and ordnance reports show patterns. Units that fielded larger proportions of semi-automatic rifles reported fewer pauses in defensive fire, more sustained suppression during assaults, and improved ability to counter enemy counterattacks. These effects are subtle and cumulative. A single firefight is influenced by terrain, leadership, artillery, air support, morale, and countless small contingencies. But when a rifle habitually reduces the number of disorienting pauses in close exchanges across hundreds of engagements, the aggregate matters. A regiment that sustains coherent fire, while an opposing regiment staggers in the process of reloading, can hold a line, stabilize a beachhead, or buy time for maneuver. Over successive operations, those saved minutes and spared casualties change operational choices available to commanders. We must be careful with attribution. The M1 did not alone win campaigns. It did, however, alter probabilities inside engagements, in which probability often decides. The rifle's contribution was a force multiplier at the squad level and increase in effective aimed fire, and in the ability to suppress and hold that, when multiplied by thousands of squads across theaters, became a tangible factor in campaign outcomes. Veteran testimony brings this into human scale. In one composite oral history, a platoon sergeant later wrote, "We had a line of boys who knew what their rifles would do. In the first minute of trouble, that steadiness convinced men to keep their heads down. It's hard to explain when your rifle works. You think clearer." Labeled as a composite, drawn from multiple interviews, this quote captures the recurring theme. Reliability breeds confidence. Confidence steadies action, and steadiness saves lives. The rifle's performance varied by theater. In the hedgerows of Normandy, mud, cold, and extended engagements, stressed parts and dirtying accelerated gas port erosion. In the Pacific, heat and salt spray accelerated corrosion and fouling. In Korea's bitter cold springs and summer's dust created other wear patterns. Armory and contractor reports emphasize that maintenance and cleaning routines mattered. Where units kept 2 prescribed cleaning cycles and trained on immediate action drills, the M1's gas system proved remarkably resilient. Where maintenance broke down, jams and sluggish cycling increased. This interplay underscores a central truth. Technology amplifies human choices. The same mechanism that can produce a life-saving rhythm also punishes neglect. Industrial mobilization turned the Garand from a promising laboratory rifle into an army-wide tool. The conversion of shops and the scaling of supply chains were feats of wartime logistics and human coordination. Factories that had once produced farm machinery retooled for receivers. Stamping presses were redesigned to hold new tolerances. Machinists taught inexperienced hires how to read micrometers and understand heat treatment charts. Contracting systems brought private industry into coordinated production. Companies with no small arms pedigree learned to meet the armory's specifications. The result was a production system that, over the course of war, moved from experimental runs to sustained output measured in the millions. Sources vary, and estimates commonly describe total wartime production in the low to mid-millions. Exact figures are the subject of archival nuance. What matters for our argument is scale. Enough rifles reached frontline units to make squad-level changes visible across campaigns. That industrial story is also a social one. Labor pools shifted. Women and men new to precision work were trained. Towns adapted to wartime schedules. Production problems, parts that fit by hand but failed on assembly lines. Finishes that corroded in tropical shipping. Springs that loosened under prolonged fire-required engineering fixes. Supply substitutions, and new inspection protocols. The iteration that converted prototypes into thousands of identical, serviceable rifles was as decisive as the original sketch. When the rifles finally arrived on beaches and at ridgelines, their influence showed in specific, repeatable ways. On a representative Normandy morning, a squad tasked with holding a gap found that semi-automatic fire allowed them to deliver suppression, while conserving ammunition for targeted shots. In a Pacific atoll defense, a pair of machine elements and riflemen using semi-automatics could keep an enemy pinned long enough for a reinforcing platoon to cross open ground. These vignettes are composites representative reconstructions, rooted in multiple veterans. Accounts and unit reports, but they show a pattern. When small units could maintain steady, aimed fire for short windows, they bought opportunities that commanders could turn into tactical gains. We must also account for countervailing effects. The M1's en-bloc clip simplified reloading, but limited topping off. A soldier who expended 7 rounds and then reloaded with a fresh clip lost the ability to keep a partial clip topped without safe procedures. Ammunition consumption rates increased where semi-automatics proliferated, putting pressure on logistics. Commanders worried about supply lines and issued doctrine to emphasize controlled fire. Training thus became a strategic component. To harness the rifle's advantages without exhausting supply required disciplined fire control and unit-level planning. Returning now to the title's claim. Could 30 seconds decide the fate of civilization? That phrase is dramatic, but defensible as a framing device if read as a comment on cumulative effect. History rarely pivots on a single half-minute of action. It bends under the weight of many such moments. The Garen's 30-second window mattered because it occurred repeatedly, in enough engagements to tilt the balance of local fights in ways that rippled upward. Small unit cohesion, preserved by consistent brief bursts, reduced casualties, preserved unit integrity, and maintained momentum. Momentum multiplied over campaigns contributes to operational options. Options shape strategic outcomes. The rifle did not alone redraw civilization's map, but it changed the calculus inside fights that aggregated to larger shifts. To make that analytic arc tangible, let us return to the original cinematic moment and lay it alongside the mechanism that produced it. Representative reconstruction, synchronous action plus mechanism. Back on the broken dune, the camera narrows to the rifle. Each pull of the trigger sends a voice a sharp report downrange. Behind the report, invisible gas shoves into a small port. The piston receives that fleeting shove and passes it to the operating rod. The bolt rotates, moves back, throws a spent case, and the clip presents the next cartridge. The cycle completes in fractions of a second. For the soldier, the motion feels like continuity. Sights wobble slightly and settle. The trigger is pressed again. In the span of 30 seconds, that repeating mechanical event becomes a human rhythm. The squad's machine gunner finds the rhythm. The grenadier times his toss. The squad leader reads the field. That alignment, that sustained, aimed application of force, turns a chaotic ambush into a contained fight. This scene is a composite based on veteran testimony and technical records. It is not a claim that a single such moment decided a war, but a demonstration of how the mechanism and human action converged in practice. We should quantify the convergence without lapsing into false precision. Mechanically, the rifle's internal cycle could run on the order of tenths of a second under ideal, clean conditions. Human factors and the 8-round en-bloc constraint reduce continuous theoretical cycles to practical bursts. A conservative representative estimate for aimed, controlled engagements might place effective fire output per man in the 30-second window as several well-placed rounds, rather than a sustained high-rate spray. Multiply that effect by the number of equipped squads and the repetition across many contacts, and the aggregate casualty avoidance and suppression capability accumulate into operational significance. As the war progressed, post-action reports and doctrinal updates codified lessons. Manuals emphasized burst control, immediate action clearing procedures, and cleaning routines focused on the gas assembly. Ordnance notes recorded design tweaks, hardened inserts for gas ports, revised piston shapes, improved metallurgy that responded to field wear. The feedback loop between frontline use and factory engineering is instructive. Those who designed the weapon continued to listen as soldiers used it, and adjustments flowed back into production. That loop design, field use, iterative fixes where inventions become instruments that can be trusted under duress. John C. Garand watched much of this, from the vantage of the armory and the later glare of public attention. He remained, by most accounts, a modest man. He received recognition, formal commendations, and public notice that acknowledged the importance of his design, but he did not reap private fortune from it. As an armory employee, his work was the property of the government. The economic rewards that often accompany civilian patents were not part of his reality. For Garand, the measure of success was practical. The rifle worked. Men trusted it, and that trust saved lives in ways he described in letters and interviews as humbling. The moral ledger is mixed. Pride in engineering that returns men home. Sorrow for those it could not save. And the enduring question of how societies reward inventors whose creations carry both protective and destructive capacities. This ambivalence is worth pausing over. Technology that increases survivability for some simultaneously increases capacity for harm. Discussion about the M1 cannot be separated from this ethical knot. Soldiers used the rifle to survive and to fight. Commanders used it as a tool to achieve military objectives that included lethal force. Garand's own stance engineering as service captures one side of the moral equation. But public memory and institutional recompense did not fully resolve the other side. Conversations about recognition, compensation, and the commemoration of inventors who serve the public good are, in this sense, ongoing. As the final chronicle note, consider how the M1 lived beyond the war. The rifle remained in service through Korea and beyond, its basic design proving adaptable to new conditions and generations. Its presence in mid-century conflicts shaped doctrines and training that outlasted a single war. That endurance is an index of the original design's robust balance between speed, simplicity, and reliability. If the title asked an extreme question, did 30 seconds decide the fate of civilization? The more measured answer is this. 30 seconds, repeatedly and reliably delivered in critical moments, altered the balance of many fights. Those fights, in turn, shaped campaigns that helped determine the political contours of the mid-20th century. The M1 Garand did not single-handedly decide history, but it changed the probabilities inside battle in ways that mattered. So where does that leave us with John C. Garand? He remains emblematic of a particular American story. A self-educated mechanic whose patient, iterative work intersected with institutional capacity and industrial mobilization to produce a tool of great consequence. His legacy is technical and human, a design that rewarded discipline and resilience, a machine that was improved by the labor of many, and a moral reminder that inventions do not exist outside the contexts in which they are used. We close where we began, with the image of a 60-second clock that once read 30. A squad that secures 30 seconds of steady, aimed fire does not guarantee victory, but it gains options time to reorganize, to withdraw, to push forward. Time, in war, is leverage. The Garand bought small parcels of that time, again and again. Multiply those parcels across theaters, and the argument behind the dramatic title takes shape. Not a literal verdict transmitted in one burst, but a cumulative shift produced by countless 30-second windows. Comment below. Did John C. Garand receive the recognition his invention deserved? Share this video with someone who appreciates the engineering stories behind history, and tell us which aspect of the M1's story design, production, combat, or ethics you'd like us to explore next.